Okay, Algebra 2, Lesson 47. We're going to talk about graphing exponential functions. Now, a lot of this your calculator will do. It doesn't mean that you don't have to do anything, but just in all reality, calculator is going to do a lot of this because we're going to look for exact positions and things of that nature that just freehanding it isn't going to do necessarily for you. So a function of the form y equals a times b to the x is an exponential function if x, meaning my exponent, is a real number. And I want to make sure here, because, yep. Sometimes I go through and I see things that I forgot to do. A cannot equal 0, right? Because if A did equal 0, right, the whole thing would be 0, okay? B has to be greater than 0, okay? Can't be equal to it either. But b can also not be equal to 1. Okay, and you'll see all this written out on page 337 in your book. The parent function, meaning the most basic exponential function that we can make, is the function y equals b to the x, meaning that a was just equal to 1. Okay, so our parent function, we have two different types of parent functions. We have an exponential increase parent function, and we have an exponential decrease parent function. So one parent function would be y equals b, where b is greater than 1. And we have the parent function y equals b, where b is greater than 0, but it's less than 1. What types of numbers are greater than 0 but less than 1? Decimals are, for sure. Also, fractions that are less than 1 would count. That are still decimals, but just a different format. They're typically, and the reason I bring up fractions is because that's typically how they're going to be shown. So like y equals, 1/4. And I don't know, did I forget to put in? Yeah, I did. Yeah. And so these aren't just y equals b, but let me go ahead and fix this so that we see it. There's more to it than that. It's y equals b to the x. So it's not just y equals b, but also y equals b, where b is a decimal or a fraction to the x. Okay? So b could be a whole number or even a mixed number, right? Just so long as it's greater than 1 to the x, and I would get an exponential increase. But my parent function for exponential decrease has a somewhat limited range. Okay? And there was really no good way for me to draw, so I had to do it by hand, and I was doing it with like a mouse, and so it wasn't even all that smooth. So that's why it looks a little squiggly. But for each graph above, the line y equals 0, or the x-axis, is what we call an asymptote. Okay, y equals 0 is the x-axis. Do we remember that? Okay, so it's the same thing. So I'm not showing you two different things, but that's what they mean by asymptote is that it approaches it but never actually touches it. Okay, so in my picture, yeah, I mean you could see where it touches, but it should come just like ever so close to it, and it will continue to get closer and closer and closer to it, but it'll never get there. Okay, does that make sense? Right? That fraction will become infinitesimal, but it will never actually touch the line y equals 0 or the x-axis. Also, the line y equals k is a horizontal asymptote of a graph if y approaches k as x increases or decreases without bound, meaning that it may not all, in a parent function, it's going to be the x-axis, but if we were talking about something else, it could move up or down, okay? Meaning that it's just going to approach a horizontal line. It's not always necessarily the x-axis, okay? The base of an exponential function must be positive, but the exponent can be negative. All right, so we won't wind up, what they're talking about, the base is the b value, is not going to be negative. Okay, but the exponent can be negative. Okay, To graph exponential functions, we use these properties down here that we see. Okay, let me see if I can kind of bring them up so you can see. So if we had b to the negative m, that would be the same as 1 over b to the m. Okay. For example, if we had 2 to the negative third, that's the same thing as 1/2 to the third. Okay, because what's happening is that the 2 down here is getting a positive exponent as it drops below the division bar. Do we remember that property of exponents? Okay, so what that allows me to do is to keep that. Of course, we could see what type of graph is 1/2 to the third. Is that exponential increase or exponential decrease? Decrease. Why decrease? You see it now? Okay. Why?
Because
The base is what? What in this part right here? Okay. What's b and what's x? X is 1? No, x isn't 1. We have to we can scroll back up real quick so you can see. Let's go back up here. Okay, look at your parent functions. Okay, what is x in our?
Oh, it's 3.
It's 3, right? So 3 is my exponent. All right, 1/2. What is my b? 1/2. And so how do I know that this is exponential decrease?
Because it's less than 1 but greater than 2.
Right, because my b is greater than 0 but less than 1. Okay? All right, we'll get the same thing. Notice if I had 3/2 to the negative second, right, then that's going to reverse, all right? It's going to get a reciprocal, right, to the negative second. So those things are going to flip to get a positive 2, all right, which is going to give me 4/9. And make sure, let me see if I didn't, yeah, all of that looks good. All right. All right, transformation of the parent function. So we always want to be able to look at what's happening to the parent function to see, how it's being manipulated. So again, the parent function is y equals b to the x, or even, where we see a, that coefficient to b. Okay, if the absolute value of a is greater than 1, meaning that it could be negative, but if it's greater than 1, it's going to shift it vertically. So it's going to move the whole graph up. Whether it's exponential increase or exponential decrease, it's going to move it up or down. Does that make sense? Okay, so vertical shift. Okay, vertical doesn't always mean up. Okay, now if a is a fraction, so there's a fraction in front of my b value that's getting an exponent, then it's going to compress it. So it's going to change the curve of the line. Okay, so it might elongate it or might make it more steep, right? So it could make it more shallow or more steep depending upon if a is a fraction. Okay, now if a is less than 0, okay, what is anything that's less than 0? What kind of, okay, so if a is negative, okay, it's going to flip the whole thing over the x-axis. So if it looked like an exponential increase before, okay, it's going to look like this now, okay, where this is the x-axis, okay? That's if a is negative. Okay, and that's what a will always do in any parent function, is that it'll flip it across the x-axis. Okay? All right, so taking out a for a little bit here and looking at the exponent, if I, let's say in my exponent I'm subtracting from that exponent, that is going to shift it horizontally to the right so many units. And if I'm adding to the b at the end of that, right, I have a plus k, that's going to move it vertically k units. Okay? Do we understand some of that? All right. Oh, I'm sorry. There's a typo in here, and I thought that there might have been. Okay. This word shift shouldn't be shift. It should be stretch. Okay. And meaning that the K down here is what shifts it up and down. Okay, or moves it, or that moves it vertically up and down. But if A is greater than 1, it's stretching it. Okay. If A is a fraction, it's compressing it. So you have both of those things at work. Okay. So if you're writing down notes, I'm sorry, you have to go back and erase. But you'll want to do that. All right. And you'll see an example in example 3 of all of those things happening and seeing how those transformations take place. All right, so that's the end of that. Let's take a look. Okay. Let's see, 2. All right, let's look at all the different elements that we have here, and we can go back and look at those notes here in a second. What is 2 in this equation right here? What variable does it represent? Two is A. Okay. What is B? 3/5. Okay. And X is X. Okay. So going back, it said if A was greater than 1, what would it do? Do I need to go back and look at the notes? You guys should have them in front of you. All right. If the absolute value of A is greater than 1, what's it going to do to the graph? It's going to stretch it. Okay. All right. So we should see something that's stretched. Okay. 3/5. Is that a value that is that something that's greater than 1, or is it greater than 0 but less than 1? What does that do whenever it's greater than 0 but less than 1? Look at the notes. I give you that stuff not so that you'll guess later, right? But so that you can look at them and determine. When B do we see anything? Go back to like the very, let's see. It's okay. So it's going to be exponential decrease. Okay. All right. So as we come back and look at this, right, we see that this told me this was going to stretch then, right? Stretch. It helps if I can write. Stretch, decrease. Okay. So really, what are we looking at the differences between in these graphs? Am I looking at C as an option? Are we flipping it? Is there anything that tells me that I'm going to be flipping this across the x-axis? How would I flip it across the x-axis? What would have been done to have flipped it across the x-axis? Right, so if this had been -2, right, that would have given me an answer probably like B. Okay, but that didn't happen. Okay, so there's a small difference between these things. Do we see a difference between A and D at all? What's the difference? Which one is stretched? I think D is stretched. Okay. Notice in here, what's something that we can spot really quickly? If we were going to graph this in our graphing calculator, we're going to look at, what are we going to look for in the graph on our graphing calculator to determine which one of these answers is matches? I need to look for something that's easy to spot. The y-intercept, right? Because notice real quickly, because in a graphing calculator graph, I might not be able to look at the curve and see a significant difference, right? But I can see quickly the difference between where it crosses the y-axis at, correct? So if I pull open my graphing calculator and I go to y equals, okay, in this, let's see, it was 2 parentheses 3/5 to the x. Is that right? Okay. So I'm going to hit graph. Okay, that looks fine. I could zoom in, but I'm going to go ahead and I'm going to hit second graph and get a table of values. And I want to see where x equals 0 at. Oh, I'm going the wrong direction. I want to see where x equals 0. Because x equals 0 is the same thing as my y-axis, right? So where does it cross the y-axis at? 2. So which graph is correct? A is correct. So do we see how to use our graphing calculator to help us determine some of these things? Okay, and don't make quick assumptions based upon appearances. Okay? Now, the rest of this ends up somewhere else in terms of how we're solving these questions. Okay? But it uses this stuff, but it's a little different. For instance, this question 2, a lot of even like question 3, this stuff that you're going to get into in your book is actually using a formula that we haven't covered yet, but it's found in example 5. At least I'm hoping it's in your example 5. And it's this: A equals P, I'll make sure I write down this right, 1 plus R over N to the N T. Okay? So you'll see in this, P represents A, right? This 1 plus Rn is going to represent B, and this NT is going to represent X. Okay? Does that make sense? So as we look up here, Zhang borrowed $3,500 from a bank. They charge 3% interest, compounded monthly. We want to find the amount that he has to pay back after 18 years. Okay, so we want to find the amount that he has to pay back. So we're trying to solve for A. Now, he borrowed $3,500. That's the principal. Okay, $3,500. Okay, so we can already tell that this isn't going to be flipped across the x-axis, right? Because we've got a number here that's, it's a positive number. It's not a fraction, though. Okay, so it's going to be stretched. Okay, we have 1 plus, and R represents my interest rate, okay, which is 3%. So we're going to write 0.03, okay? N represents the number of times it's compounded in a year. How many times is this compounded in a year? Notice that it says compounded what? So 12 times, okay? And then we want number of times it's compounded in a year, which is 12, times the number of years. So 18. Okay? So that's what we're working with. That's what I would plug in my calculator to solve. I mean, we could scroll down and you would find it, but that's how we would set up a question like that. You're going to see some things like this in your book, unfortunately. So this would be like question E in your practice set. Okay? So you want to go back and look at example 5 to get help on that. Sorry we didn't have more time.